Hi, and welcome to this video lesson on acid and base equilibrium. So today I'm going to be discussing what acids and bases are and how to deal with them in equilibrium. So first, what is an acid and a base? Now, an acid and a base can be defined differently depending on how you need it or who you asked throughout history, but for terms of equilibrium in most things you do, the Bronsted-Lowry definition is generally the accepted definition, or the most useful, I should say. So basically, the Bronsted-Lowry definition states that an acid is a proton donor and a base is a proton acceptor. All this means is that in any given acid-base reaction, the acid will give a proton, or an H+ ion, to the base, and the base will take it from the acid. So in this reaction, you can see we have hydrochloric acid, HCl, plus water, results in H3O plus and Cl minus. So, if you see, what's happening here is this H from the HCl is being given to the water, as is displayed here, and the water is accepting it and becoming H3O+. Because the HCl has lost its hydrogen to the water, it leaves a Cl-. So in this case, the HCl has donated a proton to the water, and the water has accepted a proton from the acid. Now, another important thing to note is that because we're dealing with equilibrium, the reaction can in fact run both ways, and it does. And so, on the opposite side of the reaction, you have a different acid and a different base. And so if you want to run it this way, you see that the H3O+ gives the hydrogen ion back, and it results in HCl and H2O. So by pairing off the resulting acids and bases, so in this case these two and those two, you have what are called acid-base conjugate pairs. And basically all this means is that on one side of the equation, it's an acid, so it has the hydrogen ion, and on the opposite side, it has lost the hydrogen ion, and it becomes the base. Or in this case, it has an extra hydrogen, and it loses it here to form the base. So these are called conjugate acid-base pairs. Now, another important note for the Bronsted-Lowry definition is that everything is relative to the reaction. So what I mean by this is, if I scroll over here, this is another acid-base reaction where you have water plus ammonia resulting to form hydroxide and NH4+. Now in this case, water is donating the electron to ammonia, and ammonia is accepting it, so ammonia is the base and water is the acid. However, if we go back here, we can remember that water is the base here. So because, in this case, water is more acidic than ammonia, it's acting as the acid, and in this case it's more basic than hydrochloric acid, so it's acting as the base. So again, just remember that everything is relative to the reaction in terms of the Bronsted-Lowry definition. Now that brings us along nicely to the next point, and that's something called the autoionization of water. Now basically what this is it's a reaction that occurs between any two between liquid water molecules, and so basically all that happens is water in a very low percentage will become H+ and OH- ions, and this happens automatically in every sample of water. Let's just hide that for a second. So yeah, again, it produces H+ and OH-, and this follows the equilibrium law of mass action. What that means is that we can write an equilibrium constant for it, as I showed here. So we know that the constant for equilibrium can be rewritten as the concentration of the products raised to their exponents, where their exponents are the coefficients that go here, here, and here. And that is all divided by the concentration of the products, or of the reactants rather. So in this case, our products are OH- and H+, and they both have an exponent of 1 because there's the one that's not generally written in the equation but is there, and that's divided by the concentration of water. However, we do know, as with writing any equilibrium law, that H2O is a liquid in this case, and liquids will not be included because the concentration of a liquid is constant. So what's that mean? That means that we have a constant, and we can define it the constant of water, and that's equal to the concentration of OH minus multiplied by the concentration of H plus. Now, if you solve for this using determined values in pure water, you get a value that's approximately 1 times 10 to the negative 14. And what's awesome about this value is that it is constant for all aqueous solutions. So no matter what you're dealing with it, whether you have an aqueous acidic solution, an aqueous base solution, it will be the same. So that brings us along nicely to our first problem here. And in this problem, we're looking for the hydrogen ion concentration of a base. So let's read through this problem and see what's needed. So it says the hydroxide ion concentration in a household cleaner is 0.299 moles per liter. Calculate the hydrogen ion concentration in this cleaning solution. So our given information is we know that the hydroxide ion concentration, or the concentration of OH minus, is equal to 0.299 millimoles per liter. Now, that's the same as saying 0.299 times 10 to the negative 3 moles per liter. Okay, so what are we looking for? Well, we're trying to solve the hydrogen ion concentration. So that's the concentration of H+. Now, because we have this handy equilibrium constant for water, this is now a simple matter of plugging in values to this formula. So we know that the equilibrium constant of water is equal to the concentration of H plus times by the concentration of OH minus. So we can say that 1 times 10 to the negative 14 is equal to concentration of H plus, which is what we're solving for, multiplied by the concentration of hydroxide, which, as we solved for above, is 0.299 times 10 to the negative 3 millimoles per liter. However, generally speaking, when you're doing equilibrium problems, you just neglect the units because they will all cancel out in the end anyhow. So, the concentration of H plus is equal to 1 times 10 to the negative 14. And that will be divided by the concentration of hydroxide, which once again is 0.299 times 10 to the negative 3. And when you actually solve for that, you do the calculation, you just plug the values into your calculator, you get approximately 3.3, two significant digits, so 3.3 times 10 to the negative 11, and that's moles per liter. And that's as simple as that problem is. So let's look at another example here. This example is slightly more involved, so let's read through it. And it says, calculate the hydrogen ion concentration. So once again, we're looking for the concentration of H+. In a saturated solution of calcium hydroxide has a solubility of 6.9 millimoles per liter of solution. So we are not ever actually given an OH minus concentration. What we are given is a solubility of calcium hydroxide. So what is calcium hydroxide? Well, if you go back to a couple of years back, you know that calcium hydroxide is CaOH2. So what this is saying is that CaOH2 will react to form Ca, and again, these are 2 plus ions, plus OH minus ions, right? That's what it dissociates to form. Now, again, we need to balance this equation as we always do with chemical equations. So we have 1 Ca here, 1 Ca here. We have 2 OHs, so we need a coefficient of 2. So, with that done, we have a balanced equation. We can look into what this is actually saying. So it says that a 6.9 millimoles per liter of solution. So what that's saying is that 6.9 millimoles of solution here, of millimoles of calcium hydroxide, will dissociate in every liter of solution. So we're looking for a concentration of OH minus, and so concentration is in moles per liter as well. So you just work with the assumption that you're dealing with 1 liter. So we're going to say that 6.9 millimoles of calcium hydroxide reacts. Well, how much does that mean will form over here? If we go back to our molar ratios, we know we have a 1 to 1 to 2 ratio, so it can be seen that it'll just be 6.9 millimoles of calcium ions, because there's a 1 to 1 ratio. However, with hydroxide, it's a little bit more complex. You just have to multiply the 2, because for every 1 mole of this, there will be 2 moles of this. So to get however many moles of hydroxide are forming, you just have to multiply the number of moles calcium hydroxide by 2. So we have 2 times by the 6.9 millimoles. And again, you can just do that in your calculator or in your head, and you'll receive the 13.8 millimoles of solution, or millimoles per liter. So we now have a concentration of hydroxide, and from here, the problem is no different than the first problem that we did up here. We just plug in the values and solve. So I'm not actually going to go through that, but I'm just going to kind of recap what we have done. So again, an acid is anything that donates a proton, and a base is what accepts this proton in any reaction, and we need to remember that everything's relative to the reaction. Then we need to remember that water undergoes this process automatically, just between water ions, and it forms H plus and OH minus ions in very small ratios. This ratio can be calculated in a equilibrium constant, or Kw, which has a constant value in all aqueous solutions of 1 times 10 to the negative 14. Using this constant, we can solve for concentration of either OH minus or H plus in a given solution. Now, we're not always going to be given the concentration of one or the other, and so on occasion we may actually need to solve for that using a completed chemical formula, and then just plugging the value back in. So thank you for watching.